Thank you also for this great workshop. I think it's very timely. I was not sure what I will talk about, and I decided to talk about medical imaging. This is something that I'm pretty passionate about. We've been working on this for several years now. I will not. We don't have any, theoretical problems at this point and theoretical results. But my hope is that maybe I will convince some of you to look at this and consider, and during this summer or maybe in a year or so, we will be able to define nice theoretical problems. So before this, I wanted to say a few words about, so this again, everybody talks about extroverted algorithms. So maybe let me say a few words how I view this based on my experience. So I was lucky enough to work with many people outside of theory community. In my view, there are several, and it all reflects to the discussion on Tuesday during the panel session. Several necessary ingredients for successful introverted algorithms. One, we should have two different communities, and they should be nice to each other. Right? That's why I put this nice pictures. Right? They should be nice communities, but they also should be nice to each other. Two, we really need to build bridges. Right? And this was discussed in the panel, right? We can talk about breaking barriers or creating language, but in fact, we need to be able to create a very open and nice channel of communication. And it should be mutually beneficial, right? And usually, if we talk about our community, right, it should be probably what we can provide is nice algorithms, and what they can provide is, this is what really beneficial for us in many cases, new theoretical problems. So this means, right, that usually what I'm trying to say, maybe go for it. Extroverted is a social component, right? So it's really important to have a nice social component. You should enjoy working with people, right? Even maybe it's hard for us because many of us, including myself, are introverts, right? And but if you find nice collaborators, right, it's maybe even friendship becomes a friendship. It pays off, and the result of this extroverted algorithms are really, come after years of talking to each other. Great. So speaking about beneficial, I want to kind of maybe comment of, if we think about medical imaging, what could be beneficial for us if some of you would decide to look at this, and what could be beneficial for them. Right, so let me start with us. For us, the three motivations that at least motivates me, this is why I like to work on this. As I mentioned, I truly believe I don't have, so we have a few, we're working on them now, but I think we should be able to define many theoretical problems and even maybe new models for sublinearity, right? Maybe extending streaming or some federated learning. Two, and it gives us a clear and strong motivation for our research. And that's also a very practical question, right? Because, when we write a paper or grant proposal, it's also very important. And three, there is a tiny chance, right? This is maybe very tiny chance, but there is still a tiny chance that maybe we can impact somehow diagnostics and makes healthcare less expensive and more transparent. So what type of sublinear algorithms are needed for, at the moment, for medical imaging? Model compression, and I will try to comment why. Data compression is probably one of the biggest problems because the data is really large for medical imaging. Things like cross-silo federated learning and analytics, right? So I think most of us that looked at federated learning, right, look at cross-device, right? When we have many iPhones, right, so many phones. This is a different setting, cross-silo, it's it's in some sense more challenging, in some sense easier. And maybe most important is I would really love to try to get some kind of guarantees for approaches in machine learning. Here are some specific directions that we could try to expand our models, right? Usually in medical imaging, every element, right, in let's say in streaming model, right, every element it's just a number or a vector in high-dimensional space. Here, usually every element corresponds to a patient, right, or maybe to a sequence, to MRI sequence. So it's usually a collection of elements that are strongly correlated with each other. You can see it's maybe a path in space, things like that. And one of the biggest problems is efficient processing of the sequences. As I mentioned, federated learning. So this is really one of the biggest problems at the moment. Just sharing the data in models across hospitals, it's an open problem. As far as I understand, the current direction is to try to put everything on the cloud, but it's a debate whether or not it's going to work. And it's going to be also, expensive. Medical imaging, I think, is maybe particularly interesting for us because they very well, unlike maybe standard vision setting, right? Medical imaging is very well structured. There are only a few modalities and few types of images, and so in this case, maybe we can get better results by learning the actual distribution. But at the same time, changes inside medical imaging are very small, right? So if you try to locate a tumor, it's really a tiny fraction of the actual image, and the image is noisy, so it's maybe a standard notion of similarity will not work. And again, what is also interesting, it's usually multimodal, so it's maybe not even image together with doctor notes, image together with some variable data, and so on and so forth. So it's not even clear what kind of space we should be working. What's also important, and this is from all my collaborations, that if you decide to work on this, we need to realize that sublinear algorithms are they're very important, but usually a tiny fraction. And this is also what we discussed in the panel on Tuesday, a tiny fraction of much larger system. And so in a sense, it's humbling. And the second point is that initial approaches, and this is not only for medical imaging, as usually meat and potatoes, so something that we usually just apply existing algorithm, maybe twist it. It's mostly about engineering and so on and so forth. But in the second pass, the hope that we will get already algorithms. Okay, so the other side, how medical imaging community can benefit from us, that's actually, I think we have a very strong case. I can talk about at least 3 or 4 reasons, right? And I think it speaks to many of us, right? Actually, who has experience with United States healthcare. First of all, the cost, right? So this is a paper by Vishwa Parekh, who is my former postdoc. He's currently an assistant professor at UMD. His collaborators actually calculated the cloud cost, approximate cloud cost of radiomics in small and large practices. And let me increase this. So it could be as large as about $1 million per year, right? Which is, I think, very significant cost. Most of it comes from data, from processing data. So if we somehow magically be able to compress this even by half, right? That could decrease the cost and maybe decrease the cost to the patient. In the same realm, just dealing with the amounts of data, I didn't realize it until very recently that the medical imaging data is enormous and it's growing. And it's growing because new MRI machines are coming, right? It will be much higher resolution, so on and so forth. This is also, I was less, and again, so the reason of this talk maybe is just to make you aware of these things. I'm not sure if you're aware, but I was not aware, for example, about this. It makes sense, right, in the retrospect. There is a growing disparities based on AI. So AI should potentially minimize the disparities, but in some cases actually can increase them, right? Simply because smaller hospitals will not be able to deploy large models and so on and so forth. And last but not least, right, this is also something that I didn't realize, but if I can, I don't have any answer to this, right? But it worries me quite a bit. So AI is already here. AI is already in our healthcare, right? And you can Google more papers on this, but many patients and doctors already using it, right? FDA has approved already almost 200 AI and machine learning based devices. And I don't know if you probably heard this famous quote from Hinton in 2016 that claimed that AI claim maybe will replace radiologists in the very near future. But we also see very different claims. The recent evaluation of deep learning devices. For example, this paper looked at FDA-approved devices and found that in many cases, the performance significantly drops. Okay, and this is also another very recent paper that looked at GPT-4 even with RAG, and something that is being deployed or is supposed to be deployed in many medical settings, and found that they also don't work that much. And I guess we all had experience with generative models, right? So I tried to do something fairly simple, right? You can see that this is, so they not always do what we want them to do, right? You can also look at this, some silly things, right? Prove that E divided by 72 is the rational number and gives you a proof, right? So we all know that these things happen, but what I'm trying to say, right? This is funny. Maybe it's not that funny when it's going to be in our system, right? And it will do diagnostics for us, right? So as a community, it may be a very good idea to at least try to look at this and see if we can mitigate this or control this with some theoretical tools. Again, I have no idea how to do this at this point, but I'm happy to check it. Let me give you very two quick examples of what we've been doing in the last years. One is this collaboration with my friend Michael Jacobs, my former student Lin Yang, my students Thomas Shuhao and Vishwa, Kushbu Alireza, who's a professor at UT Health. So this was a project supported by DARPA. They wanted us to address learning at the edge, and this was related to sublinearity. But if we can learn some kind of distributed learning system where agents don't have power, don't have GPU, strong GPUs, but still want to learn by sharing the knowledge. And this was in the context of what is known as lifelong learning or continual learning. Some of you probably heard about this. In a very informal way, it can be defined as follows. We first observe, we have several tasks, different tasks. First, we observe the data for task number one and train our model just on this task. Then we observe data for task number two. And in many cases, the performance on task one will decrease. This is what is known as catastrophic forgetting. So that's what was the goal of this project. And our team tried to look at this in the context of medical imaging. I'm not going to go into details, but the idea was to try to solve different tasks where, by sharing the knowledge between agents, where every task was a different modality, different type of sequence, different type of pathology, and so on and so forth. And without going into too many details, this is what we were able to achieve. So before we started, so we, as I said, it's a kind of a meat and potato approach, right? We just took core set and applied it. We don't have any provable guarantees in this case. This is mostly engineering, right? But we were able to reduce significantly performance, the time, and communication complexity. Second example, and this is work in progress. As I said, we have sequences of images, but every image by itself is, could be compressed. And that's what this work actually started during COVID. So we were able to compress several radiological features are computed from what is known as GLCM matrix. It's an expensive computation. Again, by applying core sets, we were able to reduce time from about order of magnitude from 30 minutes to about 3 minutes. And for various types of images. Okay, if I have maybe 5 more minutes, let me say, so if medical imaging is not your type of tea, right, the same story goes with other communities. I put a particularly nice picture for computer networks, because I really like that community. They're very friendly and nice. If you ever have a chance to go to SIGCOMM, please do that. It's really, amazing community. I wrote several papers with them, and let me tell you maybe about one of these directions. This is based on the question of universal sketches that was formulated by Jelani, I think, others, right, several years ago. In a nutshell, a universal sketch is a sketch that we compute and can use later on for multiple functions, right, that we don't know ahead of time. So we had, I started this work when I was still a PhD student at UCLA. We had several results. And then in 2014, I got an email from V.S. Sekar, who I knew from his previous visit to Hopkins. And so V.S. is a very well-known researcher in computer networks. Apparently, he was excited to see this paper, and they were doing something else. So this is exactly what they were looking for. And the reason why they were looking for, because in computer networks, you see huge and very fast streams, right? You only can do very limited number of operations with every element of the stream. But you also want to calculate various statistics, and you don't even know what type of statistics you want to calculate ahead of time. Sometimes you want to do it a posteriori. Right. So it turns out that this universal sketching idea was a good approach for computer networks community. And we ended up writing a sequence of papers. The first one was UniVMon for universal monitoring, and then there's several others, a paper in security conference as well. And at the end, it has been adopted by Intel as a load balancing approach. And there was many theoretical papers by my collaborators and by many others. I guess you can talk about many additional examples, but so there was another work with, again, with DARPA and with HRL. Currently, we're also working on arrhythmia detection on a project supported by South Korean government. This is another example of data that I think where sublinear algorithms can benefit quite a lot. And the reason for this is a very large continuous streams of data, noisy data, and almost no annotations. By the way, to go back to medical imaging, right? One of the biggest open problems, in my opinion, for us is, for medical data in general, is that it's very expensive to annotate, right? If you want to even do, let's say, supervised learning, it's very expensive to annotate. So if you can compress or create some similarity measures for automatic annotations or create some kind of variant of active learning, that would be extremely beneficial. So let me stop here and see if you have any questions. Thank you.
Any questions? I actually have one question. So the course that you're computing there, is it like some specific function or how is that?
For this one, right?
The images, I think.
Yeah. So yes, it's based on. So
I think the one before.
right.
Yeah.
This one, right? Yeah. So here, what we want to compute what, let's say, for example, does not GLCM entropy. By itself, it's expensive operation, but the course, because it's based on what they call a second order approximation. So you need to essentially you need to calculate a distribution of pairs of different grade levels. And so it scales quadratically. Okay. When we do important sampling, but you can also calculate entropy on the first order, right? Just on the pixels, entropy in the neighborhood of every point, right?
Okay.
And so that's what we did. So this gives us an importance weight. We sample according to this, according basically to the importance of the first order approximation, and then calculate it only for those points.
And it has theoretical guarantees?
No, it doesn't have
Okay.
theoretical guarantees at this point. But that's for example, could be one of the initial questions. Okay. Yes.
So the common concern about applying station for medical imaging is that you'd be throwing out baby with the bathwater, right? You'll be very good in recognizing clean images, but the point is to detect anomalies. How do you kind of control for this effect?
So you're saying it will work on nice data, but it will not work on a noisy data, something.
With the actual cancers, with actual strokes.
Right. Okay. So let me put it this way. Let's start with this. The reason I am giving this talk is that at the moment I cannot even define the problem properly. Okay. So that's would be the first. I completely agree with you, but we are even in a position as a theoreticians even behind that. Right. I don't even know how to define. For example, what is the definition of a tumor? Right. In a medical, I don't know. Right. All we know at the moment is that we have sort of proxy variables that we can calculate, and like, for example, entropy, that tells us that most probably this is a tumor. At the end, our ground truth is a radiologist who will take a look at this and tell, yes, this is a tumor, this is not a tumor. So I don't know how to answer your question at this point, but I think the possible approaches that we can try is, and this is, by the way, how I think it will be used at the end. It will not replace radiologists, like I don't believe any deep learning methods will ever replace radiologists, but it will serve as a tool. For example, it will be able to identify an area where the probability of a tumor is much higher than any other. I hope it's.
So maybe to expand on this radiologist question. So first of all, an anecdote. So I spoke with one of the leading AI for radiologists kind of companies, and they share the same experience. So they don't think radiologists will be replaced,
Yes.
but they become kind of active learners.
Yes.
They have a very strong machinery. And
Yes. Absolutely.
So I'm wondering whether people in the future will kind of become more. So there will be more jobs that will revolve around active learning with machinery, with efficient machinery.
Yes. Yes. That's exactly the sentiment that I hear from my friends. Absolutely, this. The point that they're making is that you will have, as a radiologist, you will have to learn. You will have to know machine learning tools or algorithms, and radiologists with those tools will be much more powerful than radiologists without those tools. So in a sense, it will filter out people who are not capable of learning these things. And yes.
Is it restricted to radiologists, or is it other areas where it's restricted?
So I have very limited knowledge. Like everything that I know is anecdotal from my friends, right? But this is a trend, general trend in computational medicine, and this is why I showed so it's exciting, but it's also it scares me quite a bit, right? Because if you give these tools to people who don't understand them, it's I don't know how it's going to end up. But let's say with arrhythmia, right? So variable data is very different from imaging data, but the sentiment is similar, right? They really, it's very expensive. Okay, so it's even so this is much cheaper than medical, right? To collect wearable devices data, right? It's very cheap, right? We have tons of them. It's super noisy. And the annotations, so for even for this work, right, we got huge amount of data from them. Vast majority of it is not annotated, so we have no idea if there is no arrhythmia. Arrhythmia is tiny, change in the signal, right? We're not expert, we don't know anything about it. So we had to wait for several weeks for a doctor to actually look at this, because they're all busy. And yes.
Actually, to that, I just wanted to add a comment. I had lunch on Sunday with a professor at Stanford who's actually in the radiology department, and we were talking about exactly this. And he was saying that one thing that they already do now, it's not active learning. It's more like a radiologist might get a ton of images they have to read in a day, and they would like it sorted so that the more important ones that are
yes,
they get to see.
Absolutely, yes. Yes.
So they're already using basically AI to score them.
Yes. Yes. You're absolutely correct. And that's excellent. And that's exactly what giving this talk, I was hoping that you will have more lunches with radiologists and hopefully something exciting will happen. Yeah. Yes.
Maybe you have a big problem with just drying in data, but do you really have that many images? Like, I have such a hard time getting large quantities of medical data from the physicians I work with. I just wonder, how important is it to be sublinear, really? I mean, take your time and do it right, study all the data as much as you can.
Right. Yeah, this is a very good question. Yes. So it has two answers. I mean, first of all, you are correct, right? If I look at my data, let's say at the local level, like at the level of a hospital, I think you're absolutely correct, like because they already store it and you can take time and analyze it. And again, what I'm saying is anecdotal, right? This is from my conversations with my friend, but it's also, I also disagree with this, and for several reasons. Reason number one, right? the data is look at this again. I don't know. I don't know. I trust this, right? But I know that, for example, my friends are very excited about getting a new MRI machine, which gives them, I don't know, order of magnitude higher resolution, and it's happening in many hospitals. So the files themselves will grow, right? But according to the studies, right, it's also the number of images also grows with some exponential component. So in this sense, maybe it's not sublinear yet, but I think it's going to be sublinear maybe in 5 years from today.
There are no more questions. Let's thank Vova and all the speakers of the session.